Hello, and welcome to our video on the insulated properties of 3D prints based on infill pattern and density. We are Team Before.
I am Stephen Harris.
I'm Brian Ortiz.
And I'm Alex Inman. So, we are motivated by the need to replace a broken car cup holder, and so this experiment aims to identify the optimal infill density and pattern for an insulating 3D printed design. Our goal is to achieve maximum thermal efficiency while maintaining structural integrity and material efficiency. And so this created a research question of, does the infill density or pattern significantly affect the conductivity of a PLA 3D print?
So for our procedure, we will be testing 3 infill patterns: grid, concentric, and zigzag at 3 infill densities, 25%, 50%, and 75%, to evaluate thermal insulation properties. We will be fabricating 9 test cubes, 1 for each pattern density combination, and then place them on a hot plate set to 160 degrees Fahrenheit. Doing 3 cubes at a time, we will attach thermocouples to the top surface of each cube, 1 to the hot plate, to measure temperature changes. We will be recording thermal gradients over 15-minute intervals and repeat the experiment 2 additional times to ensure robust data. And we'll be analyzing the collected data to calculate the thermal conductivity coefficient for each combination. Here is our 3 infill patterns shown at the 25% infill density from a top-down view. So for our test procedure, step 1, we will be setting up the DAC in LabVIEW. Step 2, we'll be setting up the experiment, where we will plug the kilowatt voltage meter into the outlet and then plugging our hot plate into the kilowatt voltage meter. We'll be turning the hot plate onto 160 degrees Fahrenheit and allowing that to come up to temperature. We'll be placing 1 K-type thermocouple on the surface of the hot plate and the rest on the top of each cube using the high temperature tape. We'll place 3 cubes of the same infill density onto the hot plate. Step 3, for collecting data, we'll run LabVIEW for 15 minutes. We'll allow the hot plate and cubes to cool to room temperature after data collection. We will repeat that for the other 2 infill densities, and then we'll repeat the entire thing 2 more times for each set of infill densities. Step 4 will be to tidy up, where we'll clean up our lab station and the hot plate, and then we'll return all equipment. Here is the example of our experimental schematic. Here is the live view of our experimental setup. On the left is the setup for the 25% infill density cubes, and on the right is the setup for the 50% infill density cubes.
These are our sensors and instruments. We'll be using a K-type thermocouple with a temperature range of -58 to 392 degrees Fahrenheit. We will also be using a kilowatt voltage meter, which we will use to measure the current being drawn by the hot plate. We'll also use a DAC system with 16 channels for our thermocouples, as well as some high temperature tape and a hot plate. So the mathematical model we will be using is a heat transfer rate equation, both the convection and conduction versions of it. We will first solve for H with our known parameters, and we will then plug that H to find Q cubes into the heat transfer conduction equation. We will then use the Q that we find that goes into the cubes to find K, as you can see in the image below that shows a mass balance equation about the surface of the hot plate. Next up is our results. These are our graphs. On the left is a bar graph showing the average thermal conductivity based on the pattern. And on the right is a correlation graph based on the pattern and the infill density.
So for our discussion, a trend that occurred during the experiment showed that the 50% infill density for all 3 infill patterns had the lowest thermal conductance. Our initial expectations was that the thermal conductivity would decrease with the infill density on the order of the 25%, then 50%, then 75%, having the lowest conductance. During collection of experimental data, the 50% infill density category for all 3 infill patterns were the only cubes to undergo a slight melting, highlighting that they had a lower thermal conductance. So for our three hypotheses, hypothesis one is that the infill pattern will have no significant effect on conductivity. Hypothesis two is that the infill density will have no significant effect on conductivity. And hypothesis three is that the infill pattern and density will have no significant effect on conductivity. Here is our factor table. Here is our mean table. And here is our ANOVA table.
For our analysis, we cannot reject any of our hypotheses as our p is much greater than 0.05, so we lack evidence to reject any of our hypotheses.
According to our results, the infill density and pattern do not conclusively affect thermal conductance of PLA 3D prints. So based off of our calculated experimental values for thermal conductivity, using a 50% infill density with any infill pattern will offer a slightly more insulative product. But if you really want your coffee to be hot, just buy a thermal mug, unless you really don't care about insulation, in which case, use a 3D printed cup holder. So in the future, we could do more trials to get a wider range of data, use a better test rig and equipment to get more accurate data points because some of our equipment was not the most accurate, and we could also use less simplified equations to get a more complete value for our data. Here are references, and thanks for watching!